We are on.
All right, welcome to Chemistry Series. This is, by some reckoning, the 17th talk in the series, although I know somewhere in the middle things got miscounted, so we're just accepting this as 17. And we're moving on. Today, I'm going to continue with the thermodynamics talk that we started last week and just go through and clarify some of the terminology that we use in thermodynamics. I did the smart thing this time in that the slide numbers in the top right-hand corner correspond to the actual slide in the series. I gave the intro slide a number 2 so that no matter how we go, we count the slides, we end up on the same one. So slide 1 is introduction. We go to slide 2, and this is an answer to Shamasha's question from last week, that what does free energy mean? And so we have the free energy, gives free energy equation on top, and the variables in there are defined right below it. We have different types of energy, right? We have thermal energy, mechanical energy, electrical energy, all sorts of different energies. Free energy is an energy that's available to do work. In our conversation in chemical system, it's the energy that's stored in the molecules that can be released during a chemical reaction, or it actually is the internal energy of the molecule. And when that energy is released, it can do work. For example, it can heat the system or other things. So that's why it's called free energy, because it's not tied up in other forms like thermal or mechanical. So I hope that answers the question, but from really a functional point of view, that is, what do we care about? It really doesn't matter what we call this, because we just call it delta G, and then we go past that. Anyway, but that was a very good question, and as I said last week, I was really embarrassed that I didn't know the answer to that. I should have known it, but anyway, now I do, and you guys do too. So next slide, slide 3, we're going to get into some of the terms that we have heard before, but we may not know exactly what they mean. The first one is enthalpy. This is the H in the delta G equals delta H minus T delta S. H is the enthalpy. So what is enthalpy? Enthalpy is the sum of a thermodynamic system's internal energies. So it comes directly out of the first law of thermodynamics, which hopefully John can shed more light on the first law of thermodynamics. But from our perspective, our meaning synthetic chemists, first law of thermodynamics says that the change in the enthalpy of the system is equal to the heat of the system minus the work, meaning either heat that is supplied to or withdrawn from the system minus the work that is done on or done by the system. And so basically the heat of the system minus the work done gives you the internal energy of the system, and that's delta H. And below that, I've given the etymology of enthalpy, which is the heat that's within. John, do you want to say more about the first law, or is this good enough?
Kind of in the form of a question to you, Sam, because the way I think of the first law is in terms of, the internal energy, which I labeled U rather than the enthalpy H, and because U seems more fundamental to physicists, whereas H, I think you get to by adding work or something, PDV or and I'm even just trying to kind of because it's been a while since I've done this stuff. I'm trying to write out a few notes myself. But can you say a few words about the difference between enthalpy and U, which or and what you call U, which I think of as the total energy?
No, I
Okay.
can't.
Well, then maybe I'll have to come back later and try myself.
Yes. No, that's a very good question. I always kind of assumed that UNH were kind of the same thing. One was used by more of physicists than engineers. That U was more of a macro quantity, whereas H was more of a kind of a statistical mechanical uh, equivalent to U.
I
That's how I
think
always saw it.
I think that enthalpy ends up being more useful, more like the total energy for processes that are carried out at constant pressure. Does that ring any bells? And it may be wrong, but I think it's something like that.
I really don't know. I can't. I'm not going
Hey,
to.
I
Yeah,
will know soon, and then I'll clear it up maybe.
Ben's here. Ben would know. Ben knows everything. Ben, what is the difference between U and H when we're talking about thermodynamic internal energy? Basically, I assumed H and U are basically the same thing, but U is more of a macro variable, whereas H is more of a statistical mechanical variable. But they're the same thing. John is of the opinion that you have to somehow mathematically manipulate U by adding some work or something or other to get to H. Do you know the difference?
Hey guys, I didn't. How you doing? So,
Hi.
firstly, I only came into the room because I was showing my daughter some stuff, and on YouTube, this room popped up as a live room, and I said, "Hey, this is cool.
Oh,
Let
okay.
me this is a room that's going now. Let me get into it." So, the difference between what internal energy and enthalpy,
Yeah.
um, isn't the enthalpy you just take the internal energy and you add the pressure times the volume, isn't it as simple as
That's
that?
exactly, yeah,
Okay.
that is
Okay. Okay.
exactly right. And so, and I think for that reason, I mean, the thing that's really the energy of the system is U. But then for chemical processes, you add PV to that to get the enthalpy. And for reasons that I guess I'm not, and this is part of what I'm kind of hoping to get out of this, maybe we'll have to work it out together.
Well,
Chemists really like enthalpy,
yes.
even though I think it's not the energy. It's something, it's an energy, but it's not really the energy of the system because you've added the volume of the system times the pressure of the
No,
system.
but we're working under kind of constant volume pressure, right? So because volume and pressure don't change, they kind of all get wrapped into the U, and then we'll call it H.
I think it's something like that. That's kind of what I was suggesting before. There's something about the way chemists usually work that makes enthalpy more useful. Yeah.
Okay, we lost Ben. He came and dropped his pearl of wisdom, moved the conversation forward, and all right. Let's this is really what I was talking about at the beginning of last week's lecture, that the thermodynamic that a synthetic chemist looks at and does is totally different than a thermodynamic problem that a physicist or an engineer will look at, because we're not looking at bulk, right? We're not looking at the the whole water solution. What is the total energy of this solution of this thing that we got it in our calorimeter, etc. We're looking at very, very specific application of this, which is to bond energies. So as on slide 4, we'll see what I mean by when I say we look at very specific bond energies, internal molecular energies, is that we only have three types of energies in a molecule, right? We have electronic, vibrational, and translational. So translational is as the molecule rotates in the solution or moves around, is hit by other molecules, Brownian motion, etc., etc. That's translational energy. Vibrational energy is the energy within a bond, the kind of spring that we talked about at the beginning of last week, the energy inside of a bond as it vibrates back and forth. And electronic energy is something that we talked about way back in the beginning of the series, which was electrons are in a ground state, orbital ground state, meaning that that's the lowest energy that's possible for that electron. We did kind of the Hund's rule. How do you fill up the orbitals? What's the relative energy of 1s versus 2s versus 2p? And then we said, if we excite one of these electrons, meaning that if we add energy into the system, the electron can go from one ground state into a higher energy state, an excited state. And so the energies of those levels where the electrons are at, those are the electronic energies. And last week I said, we really don't talk about enthalpy or entropy or free energy as absolute things. We always talk about the changes in them, the change that occurs in those thermodynamic variables during a reaction, because there's no way for us to account for all of these electronic, vibrational, and translational energies in one molecule to be able to calculate exactly what the enthalpy of the whole system is. So what we can do is kind of say, okay, a reaction took place. What was the change in enthalpy? So on slide 5, I have shown an energy diagram that includes all three of these and tells you how they're related to each other. The two big curved lines, one lower than the other, those are the electronic energy states. The top one is the excited state. The bottom one is the ground state. So if I zap this thing with light of sufficient energy, or if I heat it, then one of the electrons from the ground state follows the blue line and jumps up to the excited state. So it absorbs energy by going up to the excited state, and then when it relaxes and comes back down to the ground state, it also emits energy. And that energy is emitted in the form of heat or light, and usually it is. It's okay, Ben. You're cool. So that it comes out as either heat or light, and we all have seen this, right? Flames are yellow. Why is that? Because the electron in the sodium that's present in the fuel, it gets heated up and jumps to a higher electronic energy state, and then relaxes back to a lower one and emits light in that yellow frequency. So this is why flames are yellows. Within each one of these electronic states, we have gradations of other energy states, and those are vibrational energy states. So you can have an excited vibrational state within the ground electronic state, or you can have an excited vibrational state in the electronic excited states. And usually when atoms absorb energy, electrons absorb energy, they go not just to an excited electronic state, but to an excited vibrational state within the excited electronic state. And first, the electron relaxes to the ground vibrational state in the excited electronic state, and then relaxes back to the ground state. And this is why the energy that's absorbed, it's not equivalent to the energy that is reflected back. So for example, that sodium atom that we were talking about, it absorbs at higher energies, but because it relaxes to the lower vibrational state, then the relaxation of electronic state gives a photon in the visible range that we see that. That's not all. Within each vibrational state, we have gradations of rotational energy states. And so we can basically get a rotational excited state within the vibrational and electronic ground states, etc., etc., etc. So these are this is why, again, it is difficult to calculate the enthalpy, because we don't know at a given time when we're calculating something if it is in an excited state, it's in the ground state, where is it in the excited state, because the rotational states go up to higher states by temperature alone. So compared to 0 Kelvin, the molecule at room temperature is in a excited rotational state, not in its ground state. It goes to the ground state at 0 Kelvin. Same thing with vibrational. So we can't really calculate those. So these energy states are the combination of these is what gives rise to the enthalpy of the molecule. I want to say something really quick. Microwave ovens, they heat things because, as you see on this, microwaves match rotational energies, but this is not totally complete, because the vibrational energies in the OH bond in the water molecule are also in the microwave range. And so when you zap the sample with microwaves, it causes greater both vibrational and rotational. So you go into more excited vibrational and rotational states, and we call that heat. So that is how a microwave oven heats your food. But for electronic, we need ionizing radiation, so like ultraviolet or gamma rays or X-rays, and that's why those cause cancer, because when an electron goes to an excited state, it tends to break the bond that it's in. Any questions so far before I move on? I know I kind of talked about a whole bunch of things. All right.
Yeah, I never heard about these vibrational and rotational thingies that electrons do. This is the very first time I hear about this.
No. The electron doesn't do that.
Oh, the electron doesn't do that.
The molecule does this.
The molecule does this, and so
Right. So the
so
molecule.
when you're heating things up, hold up a second. We are on slide 5, right?
Yes.
So these two graphs that you have are graphs of electron transitions, no?
These are the graphs of energy states that are inside a molecule. Remember, way back when we mathematically combined atomic orbitals and we made molecular orbitals out of them. We had, two atomic orbitals come in, and then we have a bonding orbital that's of lower energy and an anti-bonding orbital that's of higher energy, right? So that's a molecular orbital. This electronic transition that's taking place, it's from one molecular orbital into an excited state molecular orbital. So
I see.
all
I
of
see.
this is happening within the molecule, not within an atom.
I see. That makes more sense. Yeah. Okay. So this electron is kind of being shared by the atoms in the molecule, or by at least the two atoms that are forming the bond. And then sometimes, as it receives more energy, it starts doing all these things, and the
Yes.
molecule itself rotates, or the molecule itself does these things as a result.
No. So these are independent of each other, right? I can have excited rotational states, but no excited vibrational or electronic state. I can have excited vibrational state, but no excited electronic or rotational states, right? They're not dependent on each other. So it's the case that if I heat the sample, I'm going to excite all of these, but I'm going to excite all of these independently, not interdependently.
So Sam, maybe just to point out that on your diagram, there's lots of kind of energy things, et cetera. But at any given point, the electron may be in an excited state, which automatically means you're kind of in that upper range. And then depending on the vibrational state, it'll pick one of those lines that are shown in the upper thing. But then in addition, there's little minor gradations due to possible rotations, which also change the energy. And at some point, the energy will be a definite value, right? One, combination of all of that stuff.
Let me explain it this way. Okay. The y-axis is the energy of the molecule. Okay. I measure the energy of the molecule, and let's say it is at the bottom of the bottom well. Okay, so that's basically the ground state for everything. Then I measure the energy of the molecule, and I see that the energy of the molecule is where the blue arrow touches the top well. The question is, why did the energy of the molecule go from this bottom to that top one? For three different reasons. One is that the electron in that molecule gained more energy. One is that the vibrations in the bonds gained more energy, so they're vibrating faster at high frequency. And the other thing is that the molecule is rotating, right, at a faster pace. So all I know is the molecule itself is at a higher energy state, and now I look at the causes for the molecule being at the higher energy state, and those causes are a combination of these three kind of energy related things. Did that make sense? Or did I confuse it more?
Well, I was just to give a specific example. It's possible that the molecule would have a total energy that's somewhere between the second and third bars in the upper set of in that
No,
upper set.
no, because they're quantized.
No. But I was going to say that because what that would mean is that the electron is in the excited state. The molecule has a vibrational energy that gives you that second bar, and then there's also some rotational energy that gives you a quantized state a little bit
Yes,
above that second
yes,
bar that you haven't
yes,
shown. You just
yes,
haven't
yes,
shown it.
yes, exactly. And that's why the blue line ends up somewhere in the middle, because I have those hash marks that are at the bottom to the right of the blue mark, to the right of the red and blue mark at the bottom. I have those exact hash marks up there too. So it's going to one of those hash marks between the bigger bigger separators, which are the vibrational states.
Are we going to look on what is it that causes one or the other type, and which one is more severe? Like it needs more
No.
energy for it to happen? Okay, no.
So electronic transition is the easiest one because once you go into vibrational and rotational, you start including classical mechanics, and you're actually dealing with momentum of bodies moving in space, and so it's a little bit it takes a little bit more energy to fight the inertia there, whereas electronic transitions, you don't have that. So electronic transitions take place much more easily than vibrational or rotationals. But at room temperature where we are, it is so hot that all of these things are available to us, right? We're not really worried about that. I'm talking about going from 0 Kelvin to maybe 10 Kelvin is when we kind of see sluggish excitation of rotational states.
I'm only wondering because I just found out about this, so I'm imagining like a huge molecule, like it will take so much energy for it to rotate, whereas increasing the orbit of an electron around a certain bond should be in principle easier. But then if you imagine a smaller molecule like a H2, right? So it should be a lot easier for it to rotate. Maybe
Yes.
I'm thinking about this very naively. I don't know.
No. You're so then the enthalpy of a protein is a lot higher than the enthalpy of a hydrogen molecule because you have so much energy moving those 1,500 atoms, rotate them through space, whereas hydrogen atom, you only have 2 atoms and you're rotating through space. So because of that, then its enthalpy is a lot higher.
Thank you. That's amazing.
Sure. All right. Yeah, Ben, did you?
No, I was just gonna. I've got to dive out again because it's middle of family time again. This was really funny interaction. Of two things. One, I want to make sure that I'm come to your rooms in future. Are you running them at this time weekly? I
Yes.
really want to learn more chemistry because I was never any good at chemistry. Okay, so what? Okay, I'll put it in the diary.
So we started 40 minutes ago.
Thank you very much. I'll put that in the diary. And then the other thing was briefly before I get crucified for being on Clubhouse when I'm in with the family. I think I heard you on YouTube actually, after I popped in and then just pop out and popped in again. So it's saying something about we're not sure why there are these two energy terms, the internal energy and then the PV. Of course, PV is also energy. I think 1 liter at 1 bar, 1 atmosphere is about 100 joules. Interestingly, I seem to remember. But as I said in the chat, I think the purpose of the other term is to account for the energy the system has to do on the environment to exist in that volume. If that makes sense.
Yeah. That's correct.
Okay, yeah, that's what I thought.
But as I said, those are kind of macro, right? They're not statistical mechanical, which is what we're dealing with here.
Okay, thanks, buddy, for the clarity. I'm going to go, but I have put in the diary from next week, and I'll try and make an effort to come to your rooms in
That'd be
future because
great.
I'd love to learn more chemistry. Thank you, guys. See you soon.
Thank you. Okay.
Bye.
All right. So let's move to slide number 6. Entropy. What is entropy? This is the S term in the delta G equals delta H minus T delta S. Delta S is is the entropy. So entropy is the measure of a thermodynamic system's disorder or randomness. So where does entropy come from? I think John can give a much better explanation for this. But if you look at a ball, let's say a rock, falls to the ground, and so the rock starts out with a certain amount of potential energy. As it is coming down, that potential energy is converted to kinetic energy. When it hits the ground, that kinetic energy turns into vibrational energy of the ground molecules, and it moves out, and then it dissipates. That is what happens when a rock falls to the ground. Nothing in all the equations that describe this process tells us that the reverse can't happen. That is the energy from the surrounding can't come together, localize under the rock, and then poof, push it back up, and for it to go to the top to that potential energy. That is as far as the equations of motion, and from a Newtonian point of view, the forward process and the reverse process are exactly the same. Or planets going around the sun, whether they're going clockwise or counterclockwise, it doesn't really matter. From the equations of motion, you just change the sign. So what is it that prevents the energy from the surrounding to kind of all come together on the rock and push it up? It's randomness. That is in order to do that, you have to create a system where it becomes more and more and more and more organized, becomes more orderly, for the energy to come together. And that violates what we call the second law of thermodynamics. That is the randomness of the universe has to increase during a process. Now, this statement of randomness of the universe has to increase kind of has given rise to a lot of kind of philosophical and pseudo-philosophical and scientific and pseudoscientific bullshit. One of them is that, oh my God, this is the universe, but the universe here doesn't mean all the galaxies and all that. It could mean that, but in a thermodynamic study, system is the thing that's being studied, and universe is everything else. That's in energy communication with the system. That is it can give energy to the system or receive energy from the system. So if we have an adiabatic process, adiabatic means that there is no energy transfer between what we're doing and the outside. So bomb calorimetry, which is a highly thermally isolated device, that's an adiabatic system. So in that case, system is the reaction that we're studying. Universe is everything else inside of that bomb calorimeter. So we're not talking about galaxies and whatever when we say delta L of the universe has to be greater than 0. John, do you have anything to add to entropy?
Yeah, no, I thought that was pretty good. I mean, whenever I talk about entropy, especially in relation to the second law of thermodynamics and the things that you were talking about, I always like to point out that it is the fact that entropy maximization, that systems go toward maximum entropy, is the thing that makes movies played backwards so funny.
Yeah.
We have an intuitive understanding that the entropy of a system will maximize, and when it minimizes, it's really funny.
Yeah. So I used to always kind of hear theists criticize the second law of thermodynamics because they say, well, the formation of protein, you go from random amino acids and you make a highly ordered protein. And it's like, yeah, we're talking about the deltas of the universe, how much energy was spent, and that expenditure of energy, the release of energy to the system, the other side reactions that take place, all of that, you take that into account, you see, yeah, the formation of protein is an ordered process, but in its entirety, the universe became more disordered when we were doing that. So what do we mean by it being disordered? On slide 7, on the left-hand side, we have HCl. And on the right-hand side, we have the heterolytic cleavage of the HCl bond to give us H plus and Cl minus. This reaction as well. We saw this reaction last week as well. So on the reactant side, I only have one particle, but on the product side, H plus and Cl minus, I have 2 particles. So I have increased the randomness and the disorder in my universe, in that universe, and therefore this reaction is highly entropically favorable. So the delta S of this reaction is greater than, or it's a much greater than 0. The fact that we don't see this happening all the time, it's because it's enthalpically unfavorable, but entropically it's very favorable. We move on to slide 8. I'm going to give you another example. This time dealing with transition states. Right? We learned what a transition state was last time. It is not a molecular species. It doesn't exist. It is basically happens somewhere along the line as the bond is being broken or the bond is being formed. So top left-hand side, we saw this last week as an SN1 reaction when we talked about that we're doing these thermodynamic stuff to be able to distinguish between SN1 and SN2. So I have the SN1 reaction again on top. We said the middle one in the bracket, that's an intermediate. That is actually a molecular species. But for me, to go from the left molecule to the middle molecule, I have to walk through a transition state, and that's shown on the reaction on the top right. The transition state is when that OH2 plus, the L in that molecule is OH2 plus, is leaving. Now, as the water molecule is leaving, we are going to lose symmetry in the molecule. And so because of that, we're going to gain various additional vibrational states and rotational states for the water molecule. And that increases the randomness because we're vibrating in more different ways than we did before. We're rotating in more different ways than we did before, and the electrons that were in the bond are now freer to move around in other orbitals than they were before. So all 3 energy states that we were talking about, rotational, electronic, vibrational, entropy in those states increases. So that transition state is entropically very favorable. But if we look at the reaction in the bottom, what is happening in the transition state? On the left-hand side, at the reactant side, I have two species. I have the Nu minus and my electrophile, the carbon species. But in the transition state, I only have one, right? And so in the transition state, NU is losing a whole bunch of rotational vibration and electronic states, and so it's becoming more and more orderly, and the entire transition state is more orderly, right? We have 5 things attached to the center carbon instead of 4 with 1 floating about. So that transition state is entropically unfavorable. And slide 8. Any questions so far?
Well, I confess I didn't get that one.
Can I?
Go ahead.
I'm
Yeah.
gonna see if I get it. Okay. So we're looking at 2 examples. An example where that transition state is entropically favorable, and another example it's not entropically favorable. Now, what is a transition state? It's a theoretical state that doesn't exist in nature, but it's written in the chemical equation as you understand how the reaction is happening. So if you look on the top example, that OH2 plus, it's kind of being separated. And so as it's doing this in the transition state, it's gaining more and more freedom to move. And this kind of increases the number of microstates that this molecule can exist at before the total separation. And so as this is happening, this is entropically favorable because it is increasing the number of microstates, therefore increasing the entropy. Whereas in the bottom example, this Nu minus that you see is coming closer and closer to the nucleus, big molecule. This CXYZ is just any molecule. And so as it comes closer and closer, it's losing its energy, it's losing its freedom to rotate and move around, it's losing all those properties. And so as it's becoming closer and closer, the number of microstates of the entire system become less and less. So this is entropically unfavorable. How did I do, Sam? How did I do?
That was very good.
Oh, is it? I think maybe I might have missed a little bit about exactly what the NU and the C and the and everything
Oh
was
yeah,
going on.
that's from last
But
week. So let's let me
can I be? Yeah,
go ahead.
maybe you
Yeah,
can
yeah.
just review quickly. But is it primarily in the lower one because of the fact that the transition state has that kind of linear arrangement? Is that kind of
No,
the
no,
meat of it?
no.
No.
So
Okay.
let me explain this slide a little more to kind of refresh. So we have a compound CXYZL. Okay, CXYZL. C is carbon. XYZ are some random substituents. L is a leaving group. It's what is going to leave at the end of the reaction. So Nu is a nucleophile. It's something that has excess electrons and it's attracted to the partial positive charge on the carbon. And usually the reaction of a nucleophile with a carbon that has a leaving group results in the nucleophile replacing the leaving group. So leaving group leaves and the nucleophile goes in its place. This is called a nucleophilic substitution reaction. So there are 2 ways we can do a nucleophilic substitution reaction. One is that in the slow step of the reaction, there is only one molecule involved. That's called SN1, substitution nucleophilic first order. So in an SN1, you have the leaving group leaves. You end up with that. I'm looking at the top left equation. So in the top left equation, I have leaving group leaves. So I end up with that triangular carbon in the bracket. That's an intermediate. It's a carbocation intermediate. And now the nucleophile can come and attach itself to that carbon in a very rapid reaction. And I end up with CXYZNU. In the bottom one, that substitution nucleophilic second order, meaning that in the rate determining step, two molecules collide. That is the slow step in the reaction. In this case, the two molecules that collide are the Nu minus and the CXYZL. And this SN2 doesn't form a molecular intermediate. You know, in the top left one, the carbocation that's in a bracket, I can theoretically isolate that, bottle it, and sell it, whereas in the bottom one, the one that's in the brackets, I can't. That's a transition state. That is not a molecular species. It shows that as the nucleophile is coming in simultaneously, the leaving group is leaving. There is a point as this process is taking place that both the nucleophile and the leaving group are bonded to the carbon with bonds that are less than a full bond. Okay, so the electron is kind of flowing from Nu through carbon towards L. And somewhere along that flow of electrons, we hit the highest energy point. That's the transition state. Now in
it's good.
okay.
Did that
no,
make
go
sense?
ahead and
finish.
Okay.
I think I get it now, but go ahead and finish.
Okay. So in the top
I mean,
one,
in that point, the entropy changes in the transition states, right? So different significant from the SN1 and SN2.
yes,
Significantly influencing the relative speeds of this mechanics. I mean, that was, I'm asking to do the deeper analysis will, include calculating the actual entropy changes and using statistical mechanics approaches for more comprehensive understanding, right?
right. Right. I'm kind of talking about it in a descriptive kind of way. I'm not going to get into a statistical mechanical calculation during this series. That's like way too detailed for what we're doing here. But so let me now go back and talk about the top one again on the top right side. When L is leaving, now that has a transition state, right? Going from CXYZL to the carbocation in the middle, I'm going to have a transition state. What is that transition state? That transition state is L slowly moving away. At some point, it is at its highest energy point, and that's the transition state. And then OH2 just leaves us with the carbocation on the right. So if we compare these two transition states, I can do let me do a more rigorous explanation first, and then a much simpler explanation after that. In the top one, as the water molecule is leaving, I'm gaining additional vibrational and rotational states, right? This is what Hansen was talking about a couple of weeks ago, the application of group theory into these things, and that group theory basically tells you, based on the symmetry of the molecule, the degeneracy of the vibrational states, how many vibrational states are identical. But as I break the symmetry of the molecule, those vibrational states are no longer identical. They become unique. And so I now have a lot more vibrational states than I had before. That causes more randomness. Because it causes more randomness, then I have an entropically favorable transition state. Whereas on the bottom one, in the transition state, I have limited those freedoms, those degrees of freedom from Nu minus. Not only that, but also I have created a much more symmetrical species. This trigonal biplanar transition state that I have there has a lot more symmetry components to it than the tetrahedral structure of the reactant, and because it has more symmetry to it, then a lot more of the transitions, the vibrational states become identical, and so I lose a whole bunch of vibrational states. I become a lot more ordered, and so this is entropically unfavorable. The other thing, so this was the more rigorous explanation. The less rigorous explanation is that in the top, I have one molecule, the reactant. In the transition state, I'm on my way towards forming two molecules. So I'm becoming more disordered. Two is more disordered than one. And as I move towards making two molecules, I'm moving towards being more disordered. Whereas in the bottom one, I'm going from two molecules to one species of transition state. So I'm decreasing the randomness. I'm increasing the order of the system, so it's entropically unfavorable. I'm not going to talk about the final 3 slides because we've already gone for about an hour. I think this is enough for now. I have confused the hell out of people enough for this week. And so I'm just going to open it up for conversations, whether about this topic, other topics, whatever you want, before we
So,
bid you farewell.
so I looked into the whole enthalpy thing, and it is interesting. I mean, it's what's interesting to me is listening to you talk because it's so ingrained in a chemist that it really becomes kind of what you really do think of it as the energy of the system, but it really isn't. You do that precisely because, I mean, the enthalpy of a system is its energy plus the pressure times the volume of the system. And that's not an energy, that's just a thing that you add to the energy to get the enthalpy. But what that means is if you look at the differentials, right, you have to look because that's what you really care about. If you look at dH, you can show by comparison to the first law that du is TdS minus PdV, you can show that dH, changes in H, occur only because of changes in entropy or because of changes in pressure. So if you are working with systems at constant pressure, the only thing that can change the enthalpy is the entropy. Well, yeah.
No, no, no,
Well,
no.
I don't mean, I didn't quite say it right, but I mean, at a given, a tiny little change in the enthalpy is the current temperature times the change in entropy.
No,
So,
that's free energy. Enthalpy itself is an independent term in a free energy. So if you change the entropy, you're going to change the free energy, not
oh,
the
you're talking about in
enthalpy.
the Gibbs free energy.
Yeah, yeah,
Okay,
yeah.
that's right. So the Gibbs free energy, then, I mean, so changes in it are a change in the Gibbs free energy is the current volume times the change in pressure, which is generally 0, minus the entropy times the change in temperature. So you have the changes in Gibbs are kind of directly related to changes in temperature in a constant pressure system. That's
So we basically come back to the fact that U is H at constant pressure.
well, it's not, no, U is always H plus the pressure times volume.
Yeah, but if so then delta U equals delta H plus delta PV, and if delta PV is 0 because delta P is 0, and delta V is 0, then delta U equals delta H. That term
Okay, right.
falls
So
out.
if both the pressure and the volume are held constant, now I don't think that's usually the case, is it?
That's always the case in a chemical
Really?
reaction. Well, I mean,
In
you're
in a liquid, in an aqueous
yeah,
reaction.
you're in a solution open to the atmosphere, right? You're at constant pressure, and you're either at room temperature in a heat bath of some sort, so you're at constant temperature.
So you're talking about aqueous reactions or something, right? I
It
mean,
doesn't have to. It doesn't have to be aqueous, right? You can have organic solvents. It's still the same. That all chemical reactions are run at constant pressure,
yeah, but
even
not
if
constant volume.
and constant volume, right?
Well, how do you do that with a gas? I mean, if you have evolved gas,
Come on, you don't do gaseous reactions. Only physical chemists do gaseous reactions. Nothing useful that you synthesize and then you sell to people is done in gas phase.
okay. So, but once again, I think the point is that you are talking about aqueous react. You're not talking about reactions including
I
gases,
so I'm saying solution phase, not aqueous.
solutions. Okay, maybe
Because
I'm
because
using the wrong words.
yeah, because your solvent could
Yeah,
be an organic solvent, right? Solution based as opposed to
solution. That's
aqueous.
what I meant to
Yeah.
say, I guess.
Yeah,
Yeah.
yeah, yeah, yeah. Yeah. So I mean, I live in solution based world, right? My pressure doesn't change. Uh,
Right, but your volume either. That's the thing, right?
my
And that
volume
really
doesn't
does
change
mean,
either.
right.
My molarity changes. That's all. Moles of substance per
Right.
liter of solution, that changes.
Right. So I guess that's really the thing, right? As long as you hold both the pressure and the volume constant, then it doesn't matter whether you talk about enthalpy or energy. The
Yeah.
changes are the same, but I think the enthalpy becomes more useful. Why would that? Well, let's see, the Gibbs. So the Gibbs free energy, it has to do somehow with the way you use temperature, whether it's more
Well,
important. Oh,
because
you can measure changes in temperature.
yeah, enthalpy change, right, causes temperature change in the solution. So if enthalpy change is negative, the solution gets hotter. If enthalpy change is positive, the solution gets colder.
Oh, have to think about that more. Yeah, no, it's just interesting. It's a really different way of thinking about the same. I've been rehearsing, going through. I don't know if do you guys use Maxwell's relations and all of the the various, all the partial differential stuff, that things like that the partial of entropy with respect to volume at constant temperature is equal to the partial of pressure with respect to temperature at constant
Yeah,
volume.
physical chemists,
Yeah,
statistical mechanicists, they do all that. I
yeah.
don't, right? Because as far as I have my free energy graph, and I know what the delta G of my reaction is, what the delta H is, what the delta is, I'm done.
Uh-huh.
So,
Right.
I mean, I would like to ask something that point. A negative delta H indicates a spontaneous reaction, right? So the equation
No.
emphasizes.
Negative delta G means
Sorry,
spontaneous
yes,
reaction.
negative delta G. And in the equation emphasizes that the temperature significantly affects the spontaneity. If delta
Yes.
H is negative and the delta S is positive, right? And the reaction is likely spontaneous at all temperatures. If delta H is positive and delta S is negative, the reaction is unlikely to be spontaneous at any temperature. If both delta H and delta S are negative, the reaction will be spontaneous at the low temperatures and perhaps non-spontaneous at the high temperatures. If both delta H and delta S are positive, the reaction may or may not be spontaneous, depending on the magnitude of the delta H and the delta S, right? I mean,
Yeah,
as well as the temperature.
depends on whether delta H minus T delta S becomes becomes less than zero or greater than zero, a negative number or positive number. If it's a negative number, then it's a spontaneous reaction. So spontaneous doesn't mean that that it happens, right? It means that it happens if the activation energy is met. So, for example, wood reacting with oxygen is a spontaneous reaction, which is highly energetically favorable, but has a very high activation energy. So you have to heat the wood uh, for the reaction to take place.
I'm sorry, and entropy changes play a crucial role in that point. For let's say
Yes,
that for
absolutely.
aqueous reactions, that the changes in solvent organization, let's say that,
Yeah,
or
yeah, yeah.
interactions between the products and the water, are also important considerations in calculating delta S. Also, remember that real world situations aren't always truly constant pressure, and in these situations, that involving changes in pressure, the term the PV will impact the change in the enthalpy, in the aspects of the enthalpy, right?
If we're gas phase, yes. In solution phase, so let me back out, right? A chemical engineer has to worry about that because a chemical engineer is not operating under constant pressure and constant volume. The processes, so the difference between a chemical engineer and a chemist is that the chemist figures out what happens on the bench top, and then the chemical engineer takes that and builds a plant and makes hundreds of thousands of pounds of the thing. So when you're doing hundreds of pounds of the thing, the whole heat transfer and heats of solvation and all of these bulk thermodynamic issues that I'm not dealing with at all, they become critical for a chemical engineer because they deal with vast temperature changes, pressure changes, volume changes, right? I mean, this is why we have chemical plants that look like that. They're not just glassware on a benchtop. So all of these things that Saran was talking about and John was talking about with respect to volume and pressure and all that, if you're a chemical engineer, uh, these are of utmost importance to you, and you know these things forward and backwards. But for someone like me, who's a bench chemist and works at uh, constant pressure and volume, uh, I don't care about these things. They not that I don't. They don't get involved in what I need to do.
So, Sam, do you ever, in your work, do you ever make use of the Helmholtz free energy?
No, never.
Do you
I
know the
I,
situations in
I don't
which
even know
that
what it
is?
is.
Oh, okay. Well, so the Helmholtz free energy. So whereas enthalpy is the energy plus P times V, the Helmholtz free energy is the energy minus T times S. And so the Gibbs free energy is really kind of a combination of those, right? Gibbs you get by adding to the energy both PV, adding PV and subtracting TS. If you just subtract the TS, you get the Helmholtz free energy, and
So
if you just add the PV, you get the enthalpy.
okay, I need to read up on that.
I'm gonna, yeah,
Yeah.
right. I was just thinking to just ask. Let me just see when it's useful. And go ahead. I'll get back to you.
No, I don't know anything about it, so I don't know. So I need to kind of close the room. I'm kind of recovering from a long illness still, and so I'm pretty low energy. And so if you guys,
Energy or enthalpy, let's see.
my
You're
free
pretty low
energy,
entropy, as it sounds to
I
me.
know. Yeah, we're all geeks. Yes. Thank you very much, everyone, for being here. Next week, I'm gonna start talking about reactions and activation energies and things like that, and kind of move out of uh, kind of d- d- defining words and things like that. Talk about more interesting things. thank you all for being here. So, Shamash, what are you doing this Wednesday?
Well, thank you, Sam, for the wonderful room. This Wednesday we will be doing. We did 3 rooms about logical positivism. So if you're interested, you can brush on that before we move to this week, Karl Popper. So we're going to look at the crowd's favorite, falsification. Of course, science doesn't look to confirm. Science looks to disconfirm itself. It just looks for the counter evidence, for the proof that disproves it. That's what it looks for. So we're going to examine that idea closely, see how it holds. That's what we're going to do on Wednesday, 17:30 GMT, Philosophy Wednesdays.
Very good. I very much look forward to that. Karl Popper is one of those guys that you kind of have to know what he's talking about when you're a scientist. So,
I'm
John,
a
what are we
big
doing Friday?
Popperian. So on Friday, we're going to do episode 3 of my series, which is about my studies recently. Really, at least the things I'm finding incredibly interesting in looking at 18th and 19th century precursors to the theory of relativity, starting with the discovery of stellar aberration by James Bradley in the early 1700s. We kind of talked about just everything up before that the first week. Last week, we talked about the interpretation of stellar aberration under the then current Newtonian corpuscular view of light. Newton thought light was made of particles, and that view reigned until the early 19th century when Fresnel and others really put the wave theory on the map. And then, so we're going to look at the interpretation of stellar aberration under the wave theory and see that it kind of tightens the screws on Newtonian mechanics in a way that was saved. It was falling apart, and Fresnel came up with this kind of unsupported idea, which, if true, would save the ether by making it not possible to detect it, basically. And then, at least not to first order, as they say in V over C. But then Michelson and Morley came along and showed that you couldn't detect the ether to second order in V over C. And then the shit hit the fan. And shortly thereafter, we had relativity. And the story along the way is really interesting. I always kind of heard all these things, never really understood them, but I kind of knew where we ended up and that it was right because it works and it's verified every day. But now I really understand the arguments and the torment that physicists went through trying to figure out how to explain the experimental evidence they were gaining over those 2 centuries. And it's just, I think, a fascinating story that is probably told in a few places, but I've actually never come across a good telling of the story. So when I'm done with this, I'm going to try to put it together in a more compact way as well. Anyway, we're doing the third ep. We're going to start. We're venturing into the 19th century on Friday.
Sounds good. Thank you very much. I look forward to see everyone on all these wonderful rooms, and thank you for being here, and see you next week. I'm going to leave you with the song Midnight Lover by Mud Morganfield, who is Muddy Waters' son. The song is 7 minutes and 45 seconds. The room will end when the song ends.